Today, we're tackling a problem that challenges us to rearrange an array in a specific pattern. Given an array and a split point, can you interleave its two halves efficiently, without excessive memory use? The problem shuffle the array gives us an array, nums, and an integer n. The array consists of two halves, x1, x2, xn followed by y1, y2, in. Our goal is to rearrange it into x1, y1, x2, y2, xn, in. The core challenge is to construct this shuffled array, respecting space constraints. A straightforward approach is to declare a new list or dynamic array. We'd iterate from index 0 up to n-1. In each step, we add the current element from the first half, then the corresponding element from the second half. Finally, we convert this list back to a static array. While this correctly shuffles the elements, it requires allocating a new data structure whose size grows with the input, leading to big O of n time and big O of n space complexity for the result array and the temporary list. The key insight for optimization is that we know the exact size of our output array from the start. It will be 2 times n elements. This means we can pre-allocate a static array of that size. The pattern reveals that the element at nums sub I always goes into an even position in the result, specifically result sub 2 times I. Conversely, the element at nums sub I plus n, which is from the second half, always goes into an odd position in the result, specifically result sub 2 times I plus 1. By using this direct mapping, we can fill our pre-allocated result array in a single pass without needing any intermediate dynamic structures, making it much more space efficient. Let's trace this with nums as 2, 5, 1, 3, 4, 7 and n as 3. We declare a result array of size 6. When I is 0, num sub 0 is 2, so result sub 0 becomes 2. Num sub 0 plus 3 is num sub 3, which is 3, so result sub 1 becomes 3. Now result is 2, 3, and the rest zeros. When I is 1, num sub 1 is 5, so result sub 2 becomes 5. Num sub 1 plus 3 is num sub 4, which is 4, so result sub 3 becomes 4. Result is now 2, 3, 5, 4, and the rest zeros. Finally, for I equals 2, num sub 2 is 1, so result sub 4 becomes 1. Num sub 2 plus 3 is num sub 5, which is 7, so result sub 5 becomes 7. The loop finishes. The final result array is 2, 3, 5, 4, 1, 7. This correctly interleaves the first half of the original array with its second half, achieving the desired shuffled output. You'll spot this pattern whenever you need to rearrange elements into a new, predictable order based on their original indices, especially when you can calculate the target index directly. Another cue is when the problem asks for an in-place or constant space solution for array reordering. This optimal solution achieves big O of n time complexity because we iterate through the array once. It uses big O of 1 constant time extra space complexity, excluding the output array itself. Try similar array manipulation problems. Many follow this pattern. If you found this helpful, hit that like button and subscribe for more efficient DSA solutions.